Welcome back and welcome to session 6, Spotlight on Nutrition Analysis of Specific Food Categories. My name is Julie Eichenberger, and I will be your moderator for this last session of today. It is now my pleasure to introduce our 4 speakers for session 6. Our first presenter is Ji-Han Lee. Ms. Lee is a SNAP educator at the University of Minnesota Extension, and this is her first time attending NNDC. She will be presenting her student research, differences in the nutritional content of ready-to-eat cereals, cereal/granola bars, and savory snacks available for sale to school food service versus food retailers. Our next presenter is Dr. Lisa Harnack. She is a professor and director of the director of the University of Minnesota Nutrition Coordinating Center. She is also a member of the NNDC Executive Committee, and her talk will focus on nutrient composition variability of plant-based ground beef alternative products available in the U.S. marketplace in 2019. Next, Dr. Yin Lee is a food scientist at the Method and Application of Food Composition Laboratory of USDA and faculty at the University of Maryland, College Park. She will present co-occurrences of top ingredients and additives used in bread products in the United States. Our final speaker is Megan Edelman, who is a graduate research assistant at the University of Minnesota. She will also be presenting her student research, Dietary Fiber Content of Refined Grain Pasta is underreported in nutrient databases. For more information on the presenters, please refer to the BioSketch section of your program book. We will conclude session 6 with a Q&A session. Please drop your questions for the presenters in the Q&A box.
Hello, my name is Ji-Han. I'm from the University of Minnesota School of Public Health, and today I will be presenting differences in the nutritional content of ready-to-eat cereals, cereal granola bars, and savory snacks available for sale to school food service versus food retailers. I carried out this research for my master's project, and I'm honored to be presenting in this conference today. Federally funded nonprofit meal program, National School Lunch and Breakfast Program must meet the federal nutrition standards specified in the Healthy, Hunger-Free Kids Act of 2010. Here are the guidelines regards to calories and specific nutrients such as fat and sodium. Trans fat should be 0, and to point out that at least half of the grains must be whole grain. Some food companies may need to reformulate their products and nutrient content to be included in the school meals. These reformulated items are generally repacked to emphasize their healthier nutrient content, such as 25% low sugar. The reformulated items may be available for sale to school food operators, but the original version of the item still being sold to food retailers. Having these similar versions of item with different nutrition content raises several public health concerns and can interfere with the federal program's ability to help children establish healthy eating habits. They can mislead and cause confusion to both children and parents between items served in school food and sold in retail stores because it is difficult to differentiate the nutritional content, particularly if the school food service and retail versions have the same or similar product names. There was a report on students and parents inaccurately believing that they had seen product from school lunches in retail stores, even though these products were not sold commercially. Other study reports that school food marketing was associated with students' choice of product, which means that they were likely to consume the familiar product in retail stores. And in most cases, these products sold in retail stores have sweeter and more savory flavors than reformulated items for school. little is known about how different the reformulated products for school exist. Therefore, the purpose of this study is to identify the extent to which ready-to-eat cereal, cereal granola bar, and savory snack brands sold to school participating in the National School Lunch and Breakfast Program have formulated items differ from those brands as sold through food retail stores. To identify which reformulated items are provided to school, we selected 4 leading food companies that are in sales to food service operations. The items were listed on each company's K-12 food service product webpage. These 4 leading companies are General Mills, PepsiCo, Kellogg's, and Post. For each listed food, the full name and nutrition fact panel's information was entered into an Excel spreadsheet. We identified 3 different categories: ready-to-eat cereals, cereal granola bars, and savory snack. After collecting the information, we selected the leading food retailers that have option to order groceries online to identify matching or partial matching product available for sale. Those were Walmart, Kroger, and Walgreens. In order to be considered as a complete matching product, CMP, the product needs to have the same name as the product sold to school food service, the same name of the brand and or food company, the same brand logo and package design, the same flavor, and the same specific nutrient attributes as described on the package, such as organic, gluten-free, low, reduced, whole grain, fortified, etc. If a complete matching product cannot be identified in the 3 online retail websites, we try to find a product with the same name but without the specific nutrient attributes. We label these products as partial matching product, PMP. So for example, the left product is what we usually see in school breakfast, and the one on the right is what we would normally see in retail stores. In the case of this Cocoa Puffs, we identified the name of the product, brand, package design, and flavors the same, except that the one on the right has a different specific nutrient attribute. The left one says 25% less sugar, and the right one does not. In these cases, these items are considered partial matching products. Product information collected for both CMP and PMP includes name of the product, name of the food vendor, additional food description, availability in the retail stores, labeling as either CMP or PMP, serving sizes in grams, and percentage daily value. The following from the nutrition facts panel if available: calories, total fat, saturated fat, trans fat, cholesterol, sodium, total carbohydrates, dietary fiber, total sugar, added sugars, protein, vitamin D, calcium, iron, and potassium. These are the few examples that are partial matching products from each categories. The first one is ready-to-eat cereal and it's Cocoa Puffs. The one on the left has 25% less sugar. The product on the right is a Pop-Tart from the cereal and granola bar category. The product on the top, which is served in school food service, has the whole grain. This is another example from the Savory Snack category. The product on the left has baked, not fried, written on the package, which is very hard to notice. And the one on the right is from retail grocery webpage. If the nutrient data from the product was from the past version of the nutrition fact panels, which is before 2016, the nutrient conversions were carried out and percentage daily value was recalculated as needed, so that units and amounts were consistent to the updated nutrition facts label. Then the serving size of the products from retail stores were harmonized to the same serving size as that provided for the product on the K-12 website for analysis. In total, 158 ready-to-eat cereals, cereal granola bars, and savory snack items were located on the K-12 food service product webpage for Kellogg's, General Mills, PepsiCo, and Post. Of these products, 127 items were available for purchase in the retail stores or online, and 31 products were unavailable for purchase due to out of stock or not listed or unavailable to order. Among these items, a total of 102 items had a nutrition facts panel available. Consequently, these 102 product pairs, 85 were classified as CMP and 17 were classified as PMP. Within those 102 paired products, 83% of the products were complete matching products and 70% were partial matching products. This table is the comparison of savory snacks. Two-sided paired t-test was conducted with p-value less than 0.05 being significantly different. Significant differences in calories, total fat, and saturated fats were found in complete pair products. For example, the mean calories was 135 with a standard deviation of 47 in school products, and the mean calories of 142 with a standard deviation of 50 in retail stores. Partial matching product pairs had a significant differences in calories, total fat, saturated fat, sodium, total carbohydrates, and dietary fiber, especially if you take a look at total fat and sodium, there's a big differences than the complete matching products. Some of these nutrients, the magnitude of the differences are small, and some of the values with significant differences are the same, due to the rounding of values to the nearest whole numbers for presenting the findings. Yet, you can still see that the nutrient differences observed in school products tend to have a nutrition profile more consistent with dietary recommendations than the retail versions, being lower in calories, fat, and sodium, but higher in fibers. For cereal granola bar product pairs, there were significant differences in total fat, saturated fat, dietary fiber, total sugar, and protein, with the nutrient profile of school products generally being more consistent with the dietary recommendations compared to the retail version. For example, if you take a look at total fat, products in retail stores are the double, and so does with the saturated fat being higher in the products in retail stores. Nutrient content were similar for the complete matching product pairs. In nutrient content of complete matching ready-to-eat cereal product pairs, none of the differences were significant. However, you can still see that the mean calories and the sodium are slightly higher in the products in retail stores, and the mean fiber slightly higher in products from school. We could identify only one partial matching product, therefore no analysis was available. But as example we've seen before with the Cocoa Puffs we showed earlier, the added sugar in school products were less than retail products in partial matching pair. These numbers indicate that the nutrient content is similar or the same for most of the cereals with complete matching product names and description, and that the healthier versions are available in retail stores. The key finding for cereal, granola bar, and savory snack indicate that reformulated products are prevalent, with food items marketed to school food service generally being more consistent with dietary recommendation than products sold in retail stores. Also, Ready-to-eat cereal marketed to school food service by companies examined in this study are generally identical to similar in nutrient content to those sold to retailers. So, ready-to-eat cereals are not too worrisome compared to cereal granola bars and savory snacks. In conclusion, for some food, consider there could be differences in nutrient analysis when using food and nutrition database used to assess the diet of school-aged children or used to evaluate the nutritional quality of school menus. Also, food companies should eliminate less healthy versions of the product and provide only the healthiest product versions in both school and food retail settings to lessen the confusion and promote intake of healthier food. Thank you so much for listening to my presentation today.
It is a pleasure to be here with you today to share information on the nutrient composition variability of plant-based ground beef alternative products available in the U.S. marketplace in 2019. I'm Lisa Harnack, the director of the University of Minnesota Nutrition Coordinating Center and a professor at the university. What I'm going to do is start with some background information about plant-based ground beef alternative products, talk about the methods we did to do this nutrient analysis, share results, and discuss implications. Starting with background. Plant-based ground beef products are designed to mimic ground beef. They're designed as an option for those striving to eat a plant-based diet. They're available as both crumbles and preformed patties. Some key questions of relevance related to these products. One key question is, what are the implications for food and nutrient databases and dietary assessment tools? Do the various plant-based ground beef alternative products have similar nutrient profiles? If the answer to that is yes, that's kind of great news, because it means that when we ask people about these products, we could just ask about if they had a plant-based product, and without needing to know the brand, we just ask, how often do you eat the plant-based products, plant-based burgers, for our food frequency questionnaire. But if these products have very different nutrient profiles, then we may need to really be asking people in dietary assessment about the specific brand that they ate. And dietary assessment tools and food and nutrient databases have to, have information about the different brands versus having just a single plant-based ground beef alternative patty in the database with a single nutrient string. There's also some key nutrition questions of relevance to health professionals and consumers. One question is whether plant-based ground beef alternative products are an equivalent nutritional replacement for ground beef. In the American diet, red meat is a major source of some nutrients like iron, zinc, and vitamin B12. So if people switch to plant-based ground beef alternative products, might they expect to get the similar nutrients to what they would get from ground beef? It's possible that ground beef alternative products are more nutritious than ground beef. One reason people are aiming to eat a more plant-based diet is for health benefits. So this is a real important question. So our research objective was to evaluate the nutritional quality of a selection of plant-based ground beef alternative products available in the U.S. marketplace, and to compare it with the nutrient content of ground beef. The full findings that I'm presenting today are reported in a paper published in the Journal of Academy of Nutrition and Dietetics in 2021. So if you want to learn more and see the full findings, full results, go to that paper. Our methods, we took advantage of the fact that the University of Minnesota Nutrition Coordinating Center Food Nutrient Database was updated in 2019 in the 2019 update. We updated the plant-based meat alternative product category in the database. And just a little bit of information about this database if you don't know about it. The database aims to include leading food brands as available in the U.S. marketplace. And for commercial food products, product formulations are created by NCC database scientists based on ingredient statement and nutrition facts panel information so that nutrients beyond those listed on a product label are estimated for each product. For this analysis, we decided to focus on products in the database designed to mimic ground beef in the form of crumbles or patties. So within our plant-based meat alternative product category, we've got over 100 products. Some of them are alternatives for chicken or bacon or whatnot. So we focused in on those that were designed to mimic ground beef in either crumble or patty form. And so there were 37 products that were included in this analysis from 9 food companies. For comparison, we looked at the nutrient content of cooked ground beef with varying levels of leanness. The nutrients of focus were energy, macronutrients, phytic acid, gluten, and those nutrients for which one or more product contained 5% or more of the daily value, which turned out to be quite a few nutrients, as you'll see shortly. The nutrient comparisons were all made per 3-ounce portion. So that's standardized across the 37 products and also in comparison to the ground beef. This gives you a picture of what these 37 products were. So there was 9 brands represented. And so, for example, one of the brands was Amy's Kitchen. And Amy's Kitchen, at the time we updated the database, had 7 ground beef or patty alternative products. And I show here one example, organic black bean veggie burger. And so you can see we've got Beyond Meat, Conagra, Impossible Foods, etc. So let's jump into some key findings. This slide shows the energy and macronutrient content of plant-based products, those 37 products, and also the macronutrient content of 70%, 80%, and 90% lean ground beef. For the plant-based products, we're showing the median value across those 37 products. So for energy, the median energy content was 153 calories, which is lower than all of the ground beef, including the 90% lean ground beef. The protein content, the median was 12.6 grams per 3-ounce serving, which was lower than the ground beef. The median fat content was 6 grams, which was notably lower than even the leanest ground, the 90% lean ground beef. And the plant-based products have carbohydrates in them, a median 12.7 grams per 3-ounce serving, whereas, of course, meat has none. The variation in macronutrient intake is pretty substantial across these 37 products. So highlighted in the red box, you can see that energy ranged from 71 to 211 calories across the 37 products. Protein ranged from 4.7 to 21.8. This slide shows information on nutrients for which limited consumption is encouraged. So we're presenting here saturated fat, cholesterol, sodium, and added sugar. And all these values are as a percent of daily value. And so the median saturated fat content for the plant-based products is 4% of the daily value, which is substantially lower than even 90% lean ground beef, which is 19% of the daily value. Cholesterol is, for most products, it's 0% of the daily value. There were a few products that had, some cholesterol in them because they contained egg whites or cheese. So some of these products were not, 100% plant-based. Sodium, and obviously this was substantially lower than ground beef. For sodium, the plant-based products had a median sodium content of 18% of the daily value, which is substantially higher than ground beef. And I'm presenting added sugars here because there was a couple products that contained added sugars at the 5% of the daily value level. So it was, you can see this is very low added sugar content for the plant-based ground beef alternative products, even those that most did not contain any added sugars. When we look at the variation, there's again this wide variation across the 37 products. Thinking about saturated fat, there's products that have no saturated fat in them as a percent daily value, and ones that have as high as 30% of the daily value per 3 ounce portion, being on par with 70% lean ground beef in the saturated fat content. And we see that with sodium, there's products that range from just 2% of the daily value, which would be considered a low sodium product, to something that's 29% of the daily value, a high sodium product. This slide shows the nutrients for which the plant-based products were found to be a good or excellent source, meaning that the median percent daily value for the nutrient was greater than or equal to 10%. And so across the plant-based products, the median iron content was 10% of the daily value. So I mentioned earlier that red meats are a leading source of iron in the American diet. And so here we see that actually the median content of iron for these plant-based products is just a little bit lower than that of lean ground beef. I'm not going to go through all these nutrients, just gives you a flavor though for seeing that plant-based products on average are a good or excellent source of iron, phosphorus, manganese, copper, folate, niacin, and dietary fiber. And dietary fiber is one of those nutrients that many Americans are not consuming enough of. So that's certainly an advantage here, especially in comparison to meat, which has no fiber. Looking at that variation, we see wide variation again across the 37 products. This slide shows vitamin and minerals for which ground beef is a good or excellent source, as defined as having 10% or more of the daily value of the nutrient. And some of this is repetitive because, as I showed you in the previous slide, the plant-based products are a good, on average, a good source of iron. But they're not. But let's look at zinc. Ground beef has 48% of the daily value for zinc, whereas on the median plant-based product content is 7% of the daily value. Another one I'd like to highlight is vitamin B12. Ground beef provides 88% of the daily value of vitamin B12, and the median for the plant-based products is 0, and that makes sense because vitamin B12 is naturally occurring in foods from animal sources only. And so unless a product that's plant-based is fortified with vitamin B12, the value would be 0. In looking at this variation across products, again, we see the wide variation for all of these nutrients. And with B12, you see that there was a product that had as much as 190% of the daily value of B12, which was an instance of fortification of the product with vitamin B12. So the variation seen can be attributed to the varying ways in which these products are formulated. And here I show as an example product labels with the ingredient statement for 3 different plant-based ground beef alternative products. And so on the far left here you see an example of a product that's the second ingredient is texturized soy protein. So you can imagine that this might be a product that had a higher level of protein content, with this being the second ingredient. And its only fat source was canola oil, which is an oil that would be low in saturated fat. So this was probably a product that had low saturated fat content. Then we see this next product, which is the Beyond Burger. And pea protein isolate is the first ingredient. It contains canola oil, but also coconut oil. And coconut oil is high in saturated fat. So this, the Beyond Burger is one of those products that actually had saturated fat on par with that of ground beef. And then we see this Morningstar Farms Garden Veggie Burger. The first ingredients are water, carrots, onion, then soy flour, and egg whites, mushrooms, whole grain oats. This is a product where you can imagine that the fiber content would be, so, it's got a lot of, some vegetables in there, so you're getting some fiber, a decent amount of fiber, and but there's not an oil source that's rich in saturated fat, so this would be a product that has low saturated fat content. I mentioned that some of the products are fortified with specific nutrients, and actually the Impossible Burger is a really good example of that. This, the Impossible Burger is fortified with, as you can see from the ingredient statement here, it's fortified with vitamin E, zinc, thiamine, vitamin C, niacin, and also B12, vitamin B12. So it winds up being quite, in the case of, look at the label here, and actually this is the product that's, had quite a bit of B12, more B12 in it than ground beef. There are some limitations of our analysis. The NCC database includes leading brands only, so it doesn't represent the entire marketplace of plant-based ground beef alternative products. The nutrients are derived from nutrition facts panel and food product formulations created by NCC, not by chemical analysis of the products. To discuss conclusions, due to the wide variation in nutrient content across brands, food and nutrient databases should aim to include specific products, and dietary assessment tools should query participants for specific products eaten due to this variation. Consumers should be encouraged to read the nutrition facts panel to choose a product that best aligns with their nutrition and health goals, because again, it's not a depends upon the product as to whether it's a good source of fiber or has limited amount of sodium in it, etc. Government food assistance programs such as WIC and the National School Lunch Program may need to take into account product formulations in determining whether plant-based ground beef alternative products are suitable substitutes for meat as a protein food. Also, food companies should consider formulating their products so they align with the dietary guidelines for Americans, particularly with regard to limiting sodium content and saturated fat content. I thank you for your attention.
Hello, attendees of the 42nd National Nutrient Data Bank Conference. I'm Ying from the Method and Application of Food Composition Lab, BHNRC ARS USDA. It's a great honor to be here to talk about my work on utilizing the Ying ID framework to analyze the co-occurrences of top ingredients and additives used in bread products in the United States. I hope that after this 20 minutes journey, you will have a better understanding of what is in bread. First, I will talk about the background, some history about bread ingredients. Then I'll introduce our method to look at bread ingredients and what we learn from it. And finally, wrap up with a summary of this work. Baking has a long history in the Western diet. Western civilization is based on the cultivation of wheat. Some researchers dated it back to 6,000 years ago. Bread is regarded as a staple food and as such attracts regulation of its composition. As the society develops, the ingredients of bread may be impacted by modern science, new nutritional findings, and consumer trend. For example, in the last few decades, nutritional science findings have supported the direction of using whole grain ingredients in breads, and subsequently the optimization of ingredients and baking process. One of the examples of consumer impacts on bread ingredients was taking out of an oxidizing agent, azodicarbonamide, in breads by big food companies after a food blogger got more than 50,000 signatures in a petition drive. Bread is such an important food, and its development has been going on for thousands of years. However, to the best of our knowledge, there has not been a tool to examine the ingredients in breads, especially at national level. USDA's Global Branded Food Product Database, a result of a public-private partnership, has made publicly available the ingredient list for almost 382,000 packaged foods in the form of long text blocks. Jaspreet Ahuja has been leading the Ingredient ID project, which parses and systematically reports the ingredients used in packaged foods. This work has made the dataset of ingredients of commercial breads available for analysis. Next, let me introduce how we obtained the representative dataset for breads. There were 4 major steps involved in this process. The first step was to modify the G10 UPC codes to remove the leading 0 so that it could be matched with EAN, another set of food codes. We got more than 14,000 hits for bread products. Next, to save resources in checking accuracies of these data, we set a limit to look at foods taking up more than 0.001% of market share for the linked ones, and look for those taking up 0.1% if they were not in the branded food. This resulted in the focus of 2,328 breads, which represented over 70% of the US market. As the third step, we mainly obtained ingredient lists of breads from branded foods and manufacturer websites or distributors' websites if the data were not available through branded foods. Last but not least, we parsed ingredient text strings from the text block using an in-house program with interface looks like the left panel, and assigned parse strings with preferred descriptors and broad terms, which was also the most important and time-consuming process of the whole project. On the right panel, you could see some examples of how inconsistent and complex manufacturers reported ingredients. Not the results from the two foods on the left, but part of the 2,328 breads. The intricate design of how to treat ingredients within parentheses and what preferred descriptors to assign to the parse strings have resulted in a thesaurus and the thesaurus rule, which was iteratively updated from old versions to newer. The rest of the methods are incorporated in the results, such as use unique PDs in a food instead of multiple counts to calculate co-occurring of the ingredients. Next, let's take the 2,328 breads as a whole to analyze the status of the current bread products. Please note that the percentage here are based on the number of products, or UPCs, not the market share of them. Among the 2,328 bread products, 99 of them used the yeast. Only a few products did not list the yeast, but used sourdough culture which contain communities of living microbes. About 1% of breads did not use yeast nor sourdough culture. Some of these 100% products used leavenings. We could see that they were cornbread, gluten-free flatbread, banana bread loaf, and bread wrap from the product names. The middle chart represents the percentage of products with or without wheat ingredients. We could see that 98% of our products had wheat ingredients, and 2% of them were wheat-free, with wheat-free bread or brown rice bread in the product names. It's reported that celiac disease affects 0.5 to 1% of the general population of the United States, and gluten allergy affects 7 to 8% of children. It would be interesting to see how this percentage changed in response to consumer needs in this regard. The pie chart on the right shows the sweetness added to bread. 90% of breads contain sugar, syrup, honey, and dextrose, and 10% of them did not list sweeteners, although sugar is one of the yeast food. The Dietary Guideline for Americans 2020-2025 has continued to encourage consumption of whole grains. This table represents a snapshot of proportions of whole grain breads. All percentages in this table are based on 2,328 bread products. About 15% of the breads had this claim. A little bit over 12% of breads list ingredients in a way consistent with their whole grain claim. The fonts in purple are the product names. A little over 2% of breads used refined flours as the most abundant flour by weight. In two extreme cases, the product had the names of whole grain, but they used wheat flour or white rice starch instead. About 20% of breads used whole grain ingredients, but did not claim as whole grain products. About 8% used whole grain flour as their primary ingredient, and 13% used similar product names, but the whole grain ingredients are not their primary ingredient. The majority of breads, 65%, did not use the word whole in the ingredient list, although 4% of them can be considered using whole grain ingredient like brown rice flour or rolled oats. In a word, about 12% of the breads were whole grain products, and the rest of them are not. Next, let's look at the fortification of breads. 78% of the 2,328 top-selling products contain the word enriched in their ingredient list. 22% of them did not contain the word enriched ingredient list. Most of these 22% unenriched products contain whole in the ingredients, and the rest were plain bread. Jewish, rye bread, gluten-free breads, so only 4 to 5% of breads were not enriched or their whole grain. It is worth mentioning that none of the gluten-free breads were enriched, although some of them were whole grain products. Our previous studies on food-by-food comparison of the analytical values of protein, calcium, folate, and iron between gluten-free and gluten-containing products showed that gluten-free foods had a lot lower levels for these beneficial nutrients. After the overview of breads, let's dive into their ingredients. Let's take an overlook of the numbers of ingredients parsed from all the products. Don't let the picture of a simple bread dough fool you. There were more than 600 ingredients in breads. How did we get this number? First, after parsing of the blocks of ingredient list based on our program, there were 2,225 ingredients parsed and adopted. The non-adopted ones were explanatory words like contain 2% or less for freshness, or versus missing a comma separator that combine more than one ingredient, or some non-English words. By applying the thesaurus, synonyms get combined and grouped into 687 PDs. Among them, 228 were labeled as additive, and the rest of the almost 400 PDs were grains, fruits, starchy vegetable flours, etc. There were 61 broad terms. For additives, it was even more complicated because one chemical could be labeled for more than one function. Based on the common term, we have labeled them vitamins, sodium additive, emulsifiers, etc. The top 20 ingredients most frequently used were water, yeast, salt, wheat flour, wheat gluten, and some enriched vitamins, soybean oil, and several other additives. They were consistent with our knowledge of the basic and common ingredients among variations of breads. Some were in similar groups, such as folic acid and niacin. They were vitamins. And soy lecithin and monoglycerides, they were emulsifiers. Were they used together or in replacement of each other? To answer this question, let's look at their absolute co-occurrence. In this analysis, duplicated PDs in the same product were combined and treated as one count to avoid duplication in counting the co-occurrence of an ingredient pair. A threshold was set and resulted in the inclusion of top 22 ingredients. A heat map was plotted based on the counts. From the heat map, we can see that except for water, the highest co-occurrences are among the pairs of yeast, wheat flour, and wheat gluten, which is a feature for the bread category. From the fact that 80% products used the wheat gluten in addition to the wheat flour, we can speculate that most bakers used gluten-enhanced bread flour instead of only wheat flour to make breads. Based on this co-occurrence figure, in order to make ingredient co-occurrence more meaningful in regards of the counts of ingredient, we divide the co-occurrence count between a pair of ingredients X or Y by the total counts of each of the ingredient X or Y. We got the percentage co-occurrence table. This color intensity labeled table shows the percentage of an ingredient co-occurred with other ingredient based on columns. For example, 98% vinegar in breads co-occurred with yeast, which means almost all vinegar appeared together with yeast. On the other hand, only 44% of the yeast exists with vinegar. Previously, we mentioned the high absolute co-occurrence among the pairs of yeast, wheat flour, and wheat gluten. It appeared here that their co-occurring rates were very high too. Next, let's see the group of added vitamins. Previously, we mentioned that except for 4% of breads and some whole grain breads, the rest of bread products were enriched. Title 21 Code of Federal Regulations Part 137, Subpart 165 regulated specific levels of B vitamins and iron to include all vitamins enriched had over 96% co-occurring rate with each other. Reduced iron appeared about 78% of them, and adding other forms of iron such as elemental iron, which is the second largest count of iron form, and ferrous sulfate, the iron enrichment is also 100%. This can also be a tool to check the relative ratios of fortification of nutrients. There are 3 calcium salts appeared on our top co-occurring list. Calcium sulfite is a yeast food and dough conditioner. It was present in 64% of breads. Compared to other ingredients, monoglyceride, datum, calcium propionate, and calcium phosphate had relatively higher co-occurring rates with calcium sulfite. And the 3 calcium salts highly co-occurred with each other. It's mysterious because these emulsifiers and calcium salts do not seem to share the same functions, neither have their synergistic effects been discussed. Was this phenomenon accidental? Or there's a mechanism behind it? We don't know yet. Speaking of emulsifiers, let's look at the roles of 3 emulsifiers, soy lecithin, monoglycerides, and datum. Compared to other ingredients, these emulsifiers had higher co-occurrence rates with each other. This may indicate that the collective of manufacturers tend to use them jointly instead of excluding each other. When talking about excluding effects, we may look for the rates that are substantially lower than the presence percentage in the breads, like enzymes versus vinegar, ascorbic acid versus vinegar, enzyme versus soy lecithin, etc. Due to the time constraint, I will not discuss the excluding effect here. Let's continue with the last pair of ingredients with high co-occurrence rates that we can explain. Apparently, ascorbic acid and enzymes had high co-occurring rate with each other, which means they were used jointly. What's the mechanism behind it? Ascorbic acid is a chemical dope improver. It is oxidized by ascorbic acid oxidase, which is naturally occurring in flour. Its oxidative product, dihydroascorbic acid, will take part in the sulfonyl disulfide interaction between neighboring protein chains. Some added enzymes could convert the dihydroascorbic acid back to ascorbic acid so that it is recycled to link more neighboring proteins. There have been many efforts to optimize enzyme types to work with ascorbic acid for dough improvements. In summary, we found that 99% breads used yeast, 98% contained wheat, 90% were sweetened, and 12% were whole grain breads. We reported the highly used and co-occurring ingredients and additives. We examined the high co-occurrence rates of the group of yeast, wheat gluten, and wheat flour, and a group of enriched vitamins and iron, the group of calcium salts and emulsifiers, and a pair of ascorbic acid and enzymes. The results offered a reverse engineer thinking to analyze breads with snapshot of collective use of the ingredients overall. It may offer clinicians, researchers, and consumers information to understand key ingredients and possible trends in breads. For future work, the underlying mechanism of how these ingredients are organically connected with a thorough study. Before ending this presentation, I would like to give a big shout out to Dietary Fiber, who has been leading the ingredient ID framework. And I would like to thank Quinan and Shaila for their help. I appreciate the leadership from Dr. Pearson and Dr. Harnack, and would like to thank other lab members who helped on the ingredient ID project. I'll be happy to answer any questions you may have in a Q&A session.
Hi, my name is Megan Edelman. I'm a nutrition graduate student at the University of Minnesota, and I'm going to talk a little bit about the dietary fiber content of refined grain pasta and how it is underreported in nutrient databases. So my objectives for this project, first to evaluate the current intakes of dietary fiber in children and where those sources are coming from exactly, and then to determine the dietary fiber content of a generic brand dry enriched white spaghetti pasta using updated methods of testing for dietary fiber, and then to finally compare those results to existing values and to evaluate whether there's a need to update nutrient databases and food labels to reflect those values. So I'm going to start with just a brief overview of dietary fiber, which I'm sure will be nothing new, and then fiber needs by age and current intakes, then getting a little bit into whole grain consumption, where the sources of fiber are coming from, then different testing methods for dietary fiber and the methods that we use specifically, and then into our results and the need for updating nutrient databases and looking forward into future research. Just a very brief overview, dietary fiber defined as non-digestible carbohydrates and lignin that are intrinsic and intact in plants. So this includes hemicellulose, cellulose, lignin, oligosaccharides, pectins, gums, among others. This includes both soluble and insoluble dietary fiber. So again, soluble will be, of course, soluble in water and can help to slow digestion, lower blood glucose, and to lower blood cholesterol. And then insoluble fiber is not soluble in water, and it'll help add bulk and soften the stool. So both are found in grains and both are important. And most importantly, dietary fiber is considered a nutrient of concern in the US for both adults and children alike. So that's why it's become such a hot topic of research and ultimately why I'm talking about it today. Digging a little deeper into fiber needs by age. So as I mentioned, dietary fiber is a nutrient of concern in both adults and children, but I'm going to be just focusing on children for today. So the adequate intake value is listed as 14 grams per 1,000 kcals, and this is based on data that we have for adults. So it is a value that's also used for children, but is based off of data for adults. And then the American Health Foundation puts forth a different value of the child's age in years plus 5 grams of fiber. And the American Academy of Pediatrics states 0.5 grams per kilogram of body weight. And this is for children over 2 years. So there is a pretty wide range of potential recommendations for fiber. The problem that we see is we just don't have enough data in kids to find out what's the ideal amount that they should be consuming. So we do have to use data based on adults, which is not ideal. And not that any one of these is more widely accepted over the other, but the adequate intake is most often used. So here's a table showing USDA usual nutrient intakes from 2015 to 2018, and it's split up by age group and by males and females. So this is based off the adequate intake value and the percentage of the adequate intake that children are consuming on average. So we see that just over half of the adequate intake is being consumed by children, pretty much across all age groups. So ultimately, we just see suboptimal intakes. So why do we care? Well, there are a few potential consequences of low fiber intake. First and foremost is constipation. So this is a major concern with children. It does affect up to at least 10% of US children, and it can really affect quality of life for kids, and it can interfere with performance in school. So it's something that we want to address. And constipation, in research, it's been shown that consistent low dietary fiber intake may lead to constipation. As well, dietary fiber is among the first line of treatment for constipation. So it is important, something that we want to know more of. Where are these sources of dietary fiber and how can we help to overcome this problem? Obesity. So most of the research we have for this is actually in adults. There's very limited research in children, but we do see that with increased rates of dietary fiber intake, there are lower rates of adiposity. And type 2 diabetes, similar situation. There's actually virtually no data for kids. All of the research studies done on dietary fiber and type 2 diabetes are done on adults, but it has been shown that increased dietary fiber intake may lead to decreased insulin resistance, lower rates of high blood glucose. So it can help with that. And logically, we think, okay, dietary fiber, it helps to increase satiety and slow digestion. So if we can increase satiety, we can hopefully lower those rates of adiposity. And if we can slow digestion, we can decrease those spikes in blood glucose. So just the importance of starting from a young age, looking at the potential consequences of low dietary fiber intake. And then looking at intake of fiber from whole grain sources. So this graph shown is from NHANES data from 2003 to 2010. And as you can see, about 54.4% of fiber is coming from all grain sources. So that's both refined grain and whole grain sources. But up top, the little blue triangle, you can see that only about 15% is coming from whole grains. And this data is the same for all age groups, so both adults and children. There are some reasons for this. There are quite a few barriers to whole grain consumption. A major one for kids is preference. They tend to not like the taste and texture of whole grains. They tend to prefer refined grains over whole. Sometimes it's low availability, limited access to grocery stores with whole grain sources. A lot of times it can be costs. There is a higher price tag that comes with whole grains compared to refined grains. So it may be a preferable option for many people to purchase refined grains. It could be a lack of knowledge, whether that's a lack of knowledge about the benefits of whole grains or how to identify whole grain sources. And then finally, fad diets. So this is something that's become increasingly popular in recent years. Things like a gluten-free diet or a ketogenic diet, and all of these are kind of represented by a push away from grains, both refined and whole. So this could lead to a couple things. It may lead to a more negative view of grains in general by children, or it could also lead to less available grain sources in the household for parents who are following these diets. As I said, refined grains are a major contributor of fiber, so only about 15% is coming from whole grains, and then 39% of fiber is coming from refined grain sources. So typically there is a lower dietary fiber content of refined grains per serving, but we see that larger quantities and more servings are being consumed of these refined grain products by children. So that's why it becomes such a major contributor. So this just emphasizes the need to have a better understanding of how much dietary fiber these products actually can contribute in a child's diet. Moving on to our research question and hypothesis. So basically we wanted to test the dietary fiber in refined grain pasta to gain a better picture of what these types of refined grains can provide for kids in terms of fiber. And our hypothesis was that the actual fiber content of generic white enriched pastas is actually going to be greater than what is listed on the nutrition facts label for these products. Selecting our pasta, we chose a generic white enriched spaghetti pasta. So generic because the nutrient content across different generic brands is relatively consistent. That white enriched is going to be the refined grain piece of it. And then spaghetti because this is a type of pasta that is very commonly consumed among both adults and children. So it's a valuable number to know. We hoped that testing this pasta for fiber would help us to gain a more accurate picture of the fiber that this pasta can provide to children, and down the road help us to make more realistic recommendations. So although ideally we might want kids to be consuming more dietary fiber from fruits, vegetables, and whole grain sources, realistically, that's just not what we see is happening. They're consuming more quantities of these refined grains. So it's important for us to know how much is actually in these products. And we hope that it might help push back against a more negative view of pasta in general and other grains that has been developed by this fad diet culture. And then ultimately to ensure accurate values of fiber in databases for research purposes. So as I discussed earlier, we don't have a lot of data on dietary fiber and its connection to obesity and type 2 diabetes in children. So if we want to explore these connections, we need to know what actually is in the foods that kids are consuming so we can help to make these connections. Why retest if there is already a value on the label and in databases that has been accepted for years? Well, the USDA database shows that there hasn't been a new spaghetti entry since 2014 for fiber. So since then, there have been updated methods of testing for dietary fiber, and the FDA states that manufacturers are personally responsible for what is on their label. So what's listed on the nutrition facts label does have to reflect what's in the package. But the reality is that there is a lack of awareness among food manufacturers about the fact that there is new methods of testing, that the values listed in databases are outdated. So we need to update these and create more awareness so that we can get the most accurate values on the package. Digging into our methods. So we actually didn't do the testing ourselves. We sent our pasta samples off to 2 different labs, Medallion and Silicur labs, and we sent each lab a 100-gram sample of dry pasta. Both samples were identical, and they performed Codex Definition AOAC 2011.25 test, which is considered the gold standard for dietary fiber testing. So this test will quantify soluble, insoluble, as well as total dietary fiber, and it does this using an enzymatic gravimetric method and liquid chromatography. This diagram is showing the variety of different testing for dietary fiber that's out there. Some of them are a little more specialized. As you can see in the outermost circle, there are 2 tests that encompass all of the tests within the one. And the one that starred, the 2011.25, is the one that we used. So again, that quantifies insoluble, soluble, and total dietary fiber, and of both high and low molecular weight. This diagram is just a very broad overview of the Codex Definition test. So the idea is that this test is going to mimic human digestion. So we start with the dried pasta sample of 100 grams, and it goes through this process mimicking human digestion with human enzymes. And then what is left is what is resistant to digestion. So that would be the fiber. And then that goes through 2 filtration steps. The first filtration step will give us a value for gravimetric insoluble dietary fiber. The second filtration step will give us a value for gravimetric soluble dietary fiber. And then from the precipitate that's left, they'll perform high performance liquid chromatography to determine the HPLC soluble dietary fiber. So then we can add HPLC soluble fiber to gravimetric soluble fiber to get the total soluble dietary fiber. And then we add soluble to insoluble to get the total dietary fiber. So these are the results from both labs. We see that for both labs, insoluble dietary fiber was the same, 1.9 grams per 100 gram sample. And then the soluble dietary fiber was very close, it just differed by 0.2 grams. So ultimately we found that there was 5.6 grams and 5.4 grams of total dietary fiber in the 100-gram sample of pasta. So then we translate that to a 56-gram serving of pasta. That's the serving size listed on the label. And we get 3.1 grams or 3 grams per serving. Looking at the current nutrition facts label for this product, again, you can see that this is a 56-gram size serving, and there are 2 grams of dietary fiber listed on the label, so about a gram less than what we found. And just to note, this value is based on dry pasta, which is ultimately what's listed on the label has to reflect what's in the package, which is dry pasta. And then this table is comparing our values we found to the value listed in the USDA nutrient database. So per 100 gram serving, the database lists as 3.2 grams of dietary fiber, whereas we found 5.4 or 5.6 grams of dietary fiber. And then you translate to that per serving, and the USDA nutrient database has 1.792 grams per serving of pasta. So there's actually just about over a gram more of dietary fiber in a serving of pasta than what is currently listed. So a gram may seem pretty insignificant, but we talked about before how kids often consume larger quantities of these refined grains. So rather than just consuming 1 serving of spaghetti, it's pretty common for a child to consume 2 servings in one sitting or in a day. So that can add up to just over 6 grams of fiber, which could be about a third of the daily fiber recommendation, of course, depending on age and sex. So that is a pretty considerable amount of dietary fiber. Also, the FDA does state that any food item that contains 10 to 19% of the daily value of that nutrient can be listed as a good source of that nutrient. So for dietary fiber, that would be 2.8 to 5.4 grams in one serving. And again, as we found, was just over 3 grams in a serving of pasta. So now our results presented here would allow for that good source claim to be made on the label of this spaghetti product. Then finally, looking forward into future research. So we did not test whole grain pasta. We only tested refined grains. However, it would be valuable to know the amount of dietary fiber in these whole grain pastas and be able to compare the two. Also, it stands to reason that if our value for refined grain pasta was less than what it actually is, the label's showing less than actually how much dietary fiber there is in there, then it stands to reason that other grains, both refined and whole, would be outdated as well. So looking forward, definitely updating nutrient databases to reflect the most current values after more testing is done of both refined and whole grains. And then just a note, there can be a difference between the dietary fiber in dry pasta versus cooked pasta. So the NDSR nutrient database does have a value for spaghetti that's based on cooked pasta, whereas the USDA nutrient database and what's listed on the label is reflected by dry pasta. So in the future, there needs to be a little bit more consistency between databases, maybe listing a value for both dry and cooked pasta, because the cooked pasta value of dietary fiber is going to be more practical for the consumer. My acknowledgements, I would just like to say thank you to Barilla for funding. Thank you to Dr. Joanne Slavin, my advisor, for her help with this project. A big thanks to Hallie Lundquist, a peer of mine who helped immensely with the project, and to the U of M Department of Food Science and Nutrition for helping to build such a great community to foster great research.
Well, I would like to thank all of our presenters today for their great presentation.